Hello everyone, I'm Stéphane Perin and my talk today is about the evolution of prompt engineering. And before delving into the topic, a few words about me and my motivation regarding this talk. I'm currently the technical director of Inetum application services in France, and software delivery is my main line of work. And currently we are deploying generative AI technology at the group scale. And also the domain of prompt engineering is relatively recent. It is indeed evolving very rapidly, and I'm quite sure you will agree with that. I would say it's a technology evolving at an unprecedented rate. And if we look at the publication about machine learning and artificial intelligence on archive.org, for instance, the growth is exponential. So it's a pace hard to cope with. So I thought it might be interesting to take a step back and look at some patterns and theoretical background underlying the fast evolution of prompt engineering. So let's first provide some definition and theoretical framework related to those two terms, evolution and prompt engineering. And let's start with the easy one, prompt engineering. Easy one because promptengineering.rocks provide us with already a very good definition. And here it is. Prompt engineering is a cutting-edge discipline that focuses on harnessing the full potential of language models by strategically designing input instructions, prompts. So definition is quite good. I will just highlight two parts of this definition, language model on one hand and designing prompts on the other hand, because this will be the two main topics whose I will discuss evolution. And the tricky one, evolution indeed. Tricky because as you know it, Darwin got into some troubles for proposing a theory of evolution a long time ago now. But time has passed, and you may or may not know, but evolution can now be studied within a theoretical framework based on a new law of physics. And this framework is the Constructal Theory based on the Constructal law. So this law was proposed in 1996 by an American professor of Duke University, Adrian Bejan, and Professor Bejan received, in fact, the Benjamin Franklin Medal in 2018 for his discovery. And this law can really be viewed as a driver of evolution. And it states that for a finite size flow system to persist in time, to live, its configuration must evolve in such a way that it provides easier access to the currents that flow through it. So to simplify, the law said that everything around us, animate or inanimate, is usually a flow system, and that in time, the organization, the architecture of those flow systems evolve to facilitate the flowing inside them. And to give you some examples, urban traffic, your lung, when you breathe, a river, are typical flow system, and they are subject to usually two main kind of flows. One is resistive, but is a low resistive flow, and the other one is a highly resistive flow channels. And for instance, if you look at a car running fastly in the street, it will be the low resistivity flow, whereas people walking slowly in the city will be the more highly resistive flow. So in the domain of prompt engineering, we can think of many flow systems. At a high level, prompt engineering is a flow system queries flow through the model, and they will flow more or less easily depending on how well they have been crafted. Okay, and we can also look deeper into the engine. The encoder-decoder architecture, for instance, we have information flowing, and the encoder compresses the input sequence, and it's something probably more straightforward, so low resistivity flow. And the decoder is probably more complicated, so can consider it a high resistive flow. And one last example, for instance, during the generative model sampling, you have token probabilities flowing with probably more resistance for the low probability tokens, words that are more rare, whereas common words will more easily come and are considered high probability, low resistive flow. Okay, these are just some examples to be further explored and validated, but it gives you the idea. And constructal theories come from mechanical engineering and non-equilibrium thermodynamics. And it is a point interesting to notice because thermodynamics had been a long-lasting source of inspiration for machine learning. I give you an example. If we look at the model behind most text-to-image generative AI, such as DALL-E or Midjourney or the model from Stable Diffusion, then if you look at how they work, and I'll give you an example here, you probably are quite used to this kind of system, but you see that once received, my prompt is progressively computed, and the uniform background progressively is denoised as more and more details appear, and the image becomes more photorealistic until the final state is reached. And this kind of process is indeed inspired from thermodynamics. So you see that we are not so far from our domain when I put constructal theory into the equation. For instance, one of the seminal papers in that matter in 2015 was entitled Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. So after this introduction and some background, let's see where constructal theory might fit in the evolution of prompting patterns and LLM reasonings. You probably know that LLMs are considered zero-shot reasoners. The reason is that the model defines the next more probable token given an input. So they are initially not very good at arithmetics, for instance, as exemplified here, where a simple calculation is not performed correctly. So the next step is to try to get more relevant answers by teaching through a few examples an approach called few-shot prompting. So it works very well with different use cases, such as classification, but still not very well for computation, for arithmetics. So the next evolutionary step here consists to exemplify the reasoning mode. So in this case, the LLM is able to learn from it and replicate the reasoning in subsequent queries. For instance, here you see that the model provides the correct answer, but it was provided with the logical thinking to reproduce. Okay, so this is an approach called chain of thoughts. It has become very frequent, and also the system can be improved. Several parallel reasoning lines can be processed and then followed by a majority vote on the most probable result. Okay. This is how self-consistency was added to the previous chain of thoughts. So it's called chain of thoughts with self-consistency. And here you see in the example that you have 2 times the same result. So this one is considered more consistent and is provided as output. And eventually a new pattern emerges with the 3 of thoughts. So, and if you had been trained like me on a previous generation of AI in the 90s, you will certainly recognize here the backtracking approach implemented, for instance, in Prolog or the so-called expert systems of the time. So in the case of 3 of thoughts, what we have is the chaining of thoughts is now arranged in a 3-shape structure. And then the reasoning will recursively explore the tree, but stop and resume in another branch as soon as a non-consistent result is found. As displayed here, with an impossibility detected in the evaluation of the prompt. So of course it's more efficacious. And in this sequence, this is precisely where Constructal Theory fits, because it does not just happen by chance. In fact, 3-step structure are typical of flow system balancing flow resistivity for global better efficiency. Okay, and there is a progressive evolution toward more complexity, and the 3-shape structure emerges as an optimized approach, developing according to the second arrow of time, the Constructal law, where the first arrow of time is provided by the thermodynamics second law, also called entropy. And the story goes on. It's not the end of the story, but new models are emerging, and this recent one is a refinement of the previous 3 of thoughts approach, and it's called algorithm of thoughts. So you can expect also the approach to appear in the near future. But it's now time to look at the next example, the evolution of the size of LLMs. So some months ago, you might remember that the CEO of OpenAI, Sam Altman, told us that the age of giant models was coming to an end. And well, he's the CEO of OpenAI, so it's an opinion worth considering. But let's have a closer look at this idea. Okay. So when we look at the LLM landscape at the time, March this year, we see indeed very few very large models surrounded by a greater number of smaller models. And the question that might arise is, will the big model dominate the market, or will smaller models, less computing intensive, dominate? Well, you may have your own opinion based on your personal expertise and knowledge on the matter, but if we look at the rank size distribution of LLMs, we see there is quite a huge gap between the first one and the followers. But if we look more carefully on a bilogarithmic graph, this data seems to follow a typical pattern known as power law distribution. And this is quite a frequent phenomenon in many natural, social, or even engineered systems. For instance, in a forest ecosystem, you will probably encounter such phenomenon with the balance between a large and small system, big trees, smaller trees, bushes, grass. So this is a whole ecosystem where there is a balance between a few large and many small. And this kind of distribution is also typical of the evolution of city population distribution. It exhibits this kind of power law distribution, and even more interesting is the fact that in time the distribution move upwards because well, city grow, and it also extends to the right because more cities appear on the landscape. So there is this two phenomena happening in the same time. And so what I suggest here is that because the landscape of LLMs is a kind of ecosystem with many LLMs being part of the same evolutionary tree, I think we should probably see the same trends in the data distribution. So it means that in time there will be probably some few more bigger model that will appear. Okay, so the distribution will shift up, but it will also extend to the right because more smaller model will appear, and probably makes sense because these very huge model that are very expensive to train. So only a few companies, states, group of interest may be able to invest in such training cost, whereas many smaller and also more specialized models might appear to target niche markets, in fact. So this is a kind of prediction, but it might take that the age of giant model is not totally over yet. And finally, my last example will concern the generation of software programs thanks to generative AI. And 2 years ago already, the ability of generative AI to generate software code was, I would say, advertised. But soon after, critics started also to appear. And here in the IEEE spectrum, we are told that coding with ChatGPT, GitHub Copilot, and other AI tool is both irresistible and dangerous. And of course, I agree, because the code produced can contain hallucinations, security vulnerabilities, errors, non-efficient implementation, also intellectual property rights issues, and the list goes on. Okay. But also 2 years ago already, a group of researchers investigated the usefulness of such incorrect software programs, and the conclusion is that somewhat unexpected. So I quote, "Contrary to expectation, software engineers felt a generative model that produced imperfect output, such as code with compilation or logical errors, will be a useful head." So the publication is entitled "Perfection Not Required," and I'm particularly fond of this title because it provides me with a direct link, once again, with Constructal Theory. Because for this theory, perfection is considered the enemy of evolution. As Professor Bejan says, the advantage of not being precise is more freedom to change. So it's precisely the imperfection of a system that make it more resilient by allowing freedom to change and adapt. So it makes sense when you see a developer using an AI code assistant. Regarding the code proposed, what is good is kept, what is useless is removed, and what is wrong is fixed. This concludes my example, and to end my presentation, I will try to formulate some takeaway and give one last perspective. So I tried to show you that prompt engineering is a flow system, and it contains also many sub-flow systems, and that its evolution shows typical flow patterns. For this reason, I think that we can use a theoretical framework such as the Constructal Theory to better grasp the fast evolving landscape of prompt engineering and generative AI in general. Finally, and probably an important lesson, is that we learn that imperfection offers opportunities and freedom to change. And I think that since my presentation was probably far from being perfect, I'm sure our discussion will offer me many improvement opportunities. And I also think that I owe Professor Bejan the last word. So I will use one of his famous quotes. The evolution of human and machine species is oriented in time from the naked man to the man with progressively more powerful add-ons, artifacts, contrivance, devices, machines, science. And you will probably agree that we are now witnessing the rise of the human and generative AI species powered by prompt engineering. So I'm Steven, and I presented you my talk, Navigating the Evolution of Prompt Engineering, and see you in the discussion room.